There we go. Welcome to this presentation on authorization strategies in GraphOS. We're going to look especially at Apollo Router and its external co-processing feature. And in this presentation, we'll also look at how to implement that feature with Open Policy Agent in order to have flexible and fine-grained, context-aware, very client-based, attribute-based authorization policies for your Supergraph, right at the edge of your GraphQL APIs. As Trevor said, my name is Jay Barr, Senior Technical Product Manager at T-Mobile. My co-presenter is Manoj Sukumaran, who is Principal Architect at T-Mobile. Manoj also leads our GraphOS team on best practices and governance standards for our graph. And together we're excited to present the challenges and solutions we've had with authorization in our graph. But first, I want to, I got to learn how to click. I want to talk about a couple of broad terms, probably some review for a lot of you, but when we're securing an API, generally there's two broad terms that we talk about when we talk about accessing that API. One is Authn, or authentication, and the other is AuthZ, authorization. Authentication has to do with identity. Who am I? Who I claim to be? So these are, your passwords, your multi-factor authentication, are all Authn sorts of things. Authorization is then what that authenticated user can do on your API. What permissions do they have? What data can they access? What can they change, delete, add on your API? And as an analogy for that, just to kind of bring it home, let's say I book a flight somewhere, maybe to a GraphQL summit in San Diego or something. And the day comes, I go to the airport, I check my bag, and I get on the flight, right? No, I have to first pass through security. And TSA is going to want to look at my driver's license, maybe my passport, maybe just facial recognition nowadays, to verify that I am who I say I am. But that's not it, right? They're still not going to let me back to the gates because I also have to have my boarding pass, which is now my permission to get back to the gates. And so I'll need both authentication and authorization to be able to get past TSA, back into the gates, and board a particular flight. Not just any old flight I want to, but I'm only permitted to board a specific flight and take that home. GraphQL has tools for both of these things. Even in the router, it's easy with Authn, just some easy configs to verify JOTs and using JOT keys, different IDPs to verify Authn. And AuthZ, there are a lot of tools and a lot of other little seminars, one right after this that sounds tasty on peanut butter and chocolate or whatever, so that talk about AuthZ. But we needed something that was at the very edge of the graph in the router that could be client-based. We have lots of micro front ends that have access to our API, lots of different, even external API users. And each of those has a different kind of data fingerprint that they need, different access that they need to our Supergraph. And we wanted to have a way to filter that and to give all those different users particular access to that Supergraph right at the router. So directives weren't going to work very well for us because that's all at a subgraph level to place things like requires scope or at policy or tags for a contract. All of that would involve our subgraph teams getting very involved with that. Contracts also would mean that for each of those thousands of clients, we were going to be spinning up multiple router instances, which is there's a cost and there's a load to have all those services running, all those router services running. No, we wanted something where we could have that client-based, fine-grained, very attuned to the client token attributes right at the very edge of the router. Manoj is going to tell us a little bit more about that. Manoj.
Thanks, Jay. That's a great introduction to authentication and authorization. In GraphQL, we have a single post endpoint that gives access to the Supergraph. In the Supergraph, the operations, the query, the mutations, and the underlying data types can be accessed through this single endpoint. Now, is it sufficient if we secure that endpoint with only authentication? What happens if a client who gets access to that endpoint is completely authenticated? In that case, they can access any of the operations or any of the data types. So it's a risky security model to just have authentication. We need to have authentication and authorization. How can we do that? Let's take a simple look at this one. Here we have several clients. Each client can have several micro front ends or micro apps which do some specific functions on that particular client. So based on their need, they need to access the endpoint, required to query different operations and get different data types. So we can set up authentication at the router level to make sure that only the permissioned clients get access to that endpoint. As a good security practice, we can also have authentication at the subgraph, which resolves that operation or provide the data type. Now coming to authorization, where can we do the authorization? For this case, let's assume there's a single identity provider with well-defined scopes. In that case, we can set up authorization at the subgraph level using directives. So we can have custom directives, or we can use directives like at required scopes and set up authorization. At router level, we can do that as well. In router, we can separate out the traffic based on channel or based on client through contracts. We can have separate contracts serving separate clients, thereby segregating the traffic. We can also lock down the graph, the supergraph, by providing operation safe listing using persisted queries. This can also be really effective. But what about the scenario where we have multiple identity providers and there are no defined scopes, or we want to expand our authorization to not just scopes, but more parameters, like some additional claims in the token or some authorization header attributes if we want to set up authorization policy. And what if you want to set up some specific policies based on each client? If we have to do it with the current pattern, then we need to customize it at the subgraph level. So every time a new client onboards, we need to modify the subgraph and then redeploy the subgraph, which is an operational overload. So what can be done here? So we are looking at this centralized authorization policy manager. Through this centralized authorization policy manager, the security policies can be externalized and then hosted in a centralized authorization policy manager. Authentication still remains intact. It remains in the router level as well as at the subgraph level. But we can have a policies configured per client at the centralized authorization policy manager. Again, the authorization policy manager is a decision engine which takes a decision based on the configured policies. In the policy manager, you can configure policies per client based on their IDP or the header attributes or any additional claims within the token. It is completely customizable by client. By doing this, we are externalizing the policy decisions outside of the router and the subgraphs. One more thing I wanted to stress is the authorization policy manager does not enforce the policy, but only provide the decision. The enforcement still happens at the router level, so that once if the policy is successful, the traffic is passed through. If the policy fails, the traffic is denied. So at T-Mobile, we had some very specific requirements that we were looking at for this policy manager. Let's look at those. So we wanted to set up a policy manager where we wanted to have policies configured per client in a centralized place, so that whenever a client needs access to this particular supergraph, we can set up policies and centralize it in a location so that it's easily configurable and manageable. We wanted to externalize this authorization from the code such a way that any changes in the configuration does not require redeployments and all those operational overheads. Another thing that we wanted to clearly maintain is a separation of concern, where the policy manager is acting as a decision engine, but leaves the enforcement to the router. We also wanted to set up a policy manager which can support multi-level policies for a client, meaning policies at operation level, type level, and field level. We'll look at it more in detail in the next slide. And we also wanted to have a mechanism where whenever a client onboards to the Supergraph, we wanted to have a mechanism where these clients are notified to the subgraph teams who will be resolving those the traffic, so that they are also notified upfront. As Jay mentioned, the policy manager sits at the edge of the graph. So we were looking at a more scalable authorization manager. And we also wanted to monitor the traffic that is flowing into the authorization manager, the policies that is getting applied, denied, by exporting the metrics and monitoring the inflow to the policy manager. So let me briefly touch base on what is within the policy. So in T-Mobile, we wanted to have a policy manager that where we'll be able to configure policies based on each client. For each client, we were looking at operations, a kind of an operation level policy where you can set up what all the operations that they're eligible for. And within an operation, we can go one level deeper to see what all types that they can configure. And we can also go all the way up to the attributes and set up attribute level access controls. There might be some special business logic that you want to apply for a client based on certain header parameters within that, maybe a channel or a claim or any other header attributes. Those kind of specific business case related policies can also be configured in this authorization manager. And we also might have some special use cases where, based on a role or certain parameter, we also wanted to control the depth by client in the policy manager. That can also be done. So these were some of the policies that you can set up within the policy manager. We went through the need for the centralized policy manager, what is within the policy manager. So I'd like to walk through what is a typical life cycle of a policy management. So the policy life cycle starts with the client teams requesting access to the Supergraph. So this request is passed on to the governance body, which is comprising of the the subgraph teams who own the subgraph and the operations and the data types, the platform team which runs the platform, and the security team which applies the security practices. So the request from the client is reviewed by this body, and then it translates to a policy. And this policy gets applied at the policy manager. So during runtime, when the client hits the Supergraph sends the policy check to the policy manager, and the policy decision is sent back to the router, and it gets enforced in the router. If it is allowed, it goes to the subgraphs for further execution. If it is denied, the traffic is rejected. To explain more of how to do it, I'll give it back to Jay.
Thanks, Manoj. So we need this policy manager that we've been talking about that can take this request, this GraphQL request, and look at the operations on it and say, for this client that's making this request, do they have permission for these queries, for these types, for these fields? So what were we going to use for that policy manager? There's a lot of options. There's even some vendors here today. But we chose, let me introduce you, if you haven't heard of it, to Open Policy Agent, or I like to call it OPA. So OPA is open source. It's fairly well adopted. It's kind of an industry standard. And it uses a high-level declarative language called Rego. A little tough to learn, but once you learn it, it's not too bad, where you write the policies. And so with the Rego policy language, and then the data input that can come both in real time from the runtime request that you can send to OPA, and also from other external data sources. So you can combine that data along with the Rego policies to render policy decisions at runtime right in context. So what we want to do is we want to use OPA with the router for AuthZ. And so at runtime, we'll send OPA the operation. We'll want to send it the schema to kind of verify the operation against the schema. And then we'll want to send in the auth header where it can pull the client off of maybe a JOT, a JSON web token, pull it off the audience claim or something like that to get that client ID off the Authn to then do the AuthZ work with the OPA policies. So OPA checks that auth, checks that claim, that client ID, to see if the operation, to see if the queries, the mutations, the subscriptions, the types of fields within that operation are all allowed for that client, and it returns a decision, either accept or deny in the case of our demo that we'll do. But the problem with this is that the router and OPA have some unique requirements for how they send and receive data. They're not directly compatible. So we have to introduce this interface, or what we'll call this broker service, which helps to translate, and the broker service will actually be our external coprocessor that the router will reach out to. And with this architecture, where the broker then takes the router request from the router and then sends it out to OPA, then receives that decision from OPA, and sometimes has to modify that router request, especially on a deny, and send it to the router for processing. With this architecture, we optimize query execution, because if it's denied, then it fails immediately and doesn't send anything to subgraphs. We've improved our defense in depth with the AuthZ policies, and we run this inside of, in our case, we'll run it inside of a Kubernetes pod, so that the only external access to this is into the router. That's the only ingress in, and so that there's no access to the broker service or to OPA externally once inside that pod. At different stages in its request handling lifecycle, the Apollo router can be hooked into, can be configured to send post requests to the external coprocessor. So for our OPA AuthZ handling, we're going to configure the router to send that post to that broker service at the request stage, right at the very beginning. The router service, the very first stage of the lifecycle, to send that information to the broker. So at this stage in the Apollo router, we can send the headers, the body, the SDL, basically the schema, the context, the path, and the method. For the OPA AuthZ demo we're just going to need the headers to get the auth, the body, which has the operation and the variables, and the SDL for our Supergraph schema. And so the broker receives that input from the routers, receives all of that for the external coprocessor, and it's going to transform that just slightly and then post that out to OPA. And you could include other dynamic runtime data here if you needed to, but for our case, we're just going to send the query, the schema, and the auth header to OPA for it to render a policy decision. So at the OPA service, with the Rego policy code, which kind of factors through all this data, this input object from the broker, and then these external policy data, and that's what is displayed there, OPA will render a policy decision. So this is what we've come up with for the shape of this policy data. And OPA then parses that auth header, and that's what renders in this bottom one. It's kind of describing the shape. So in the auth header, we kind of pull that client from the token attributes. It might be the audience claim, like I mentioned off your jot. In our demo, we're just using basic plain text client IDs to make it simple. And then that client ID, it's on a map, so you look that up on that key by the client ID, and it's mapped then to what are the allowed queries for this client. And then within those queries, so queries on an operation with this policy are denied by default with the policy Rego that we've written. And then within each query, you can restrict fields. So within an allowed operation, all the fields and types, all the objects within that query are allowed by default unless they're in that restricted fields object. So if OPA allows this, if OPA says, yeah, this request is allowed for this client, it all looks good, then it just basically returns the original router request to the router, and things continue normally. If OPA denies, then the router receives a break object on the control property. Instead, they're usually, if it's regular on that control property, there's just a string that says continue. But we'll replace that string with a break object that it just has this error response, which is has to follow regular GraphQL JSON object error response. In this case, just an errors array that we put the not authorized stuff. The control break object has the 401 status code which is nice too, because you can send something now other than a 200 or a 500 with this, and actually get a little more fine-grained HTTP status if you'd like to. So again, if OPA allows, the lifecycle proceeds normally, the original operation is processed according to the query plan, returned to the client. But if the router receives that break object, 401 in our case is what we put on it, and it doesn't have the continue on the control, it has the break, then the operation terminates immediately. Nothing goes to the subgraphs. Your query plan saves some time by just immediately denying this not allowed operation, and your subgraphs don't get hit. All right, so now the part I've been nervous about. No, the live demo. So I'll make this is a GitHub repo that I'll show you where it is, and totally open source. You're welcome to try to play with it after if you can. But you'll need an enterprise license for the router to have the Apollo key, the Apollo graph ref. There is also Gateway on this demo too that also has an AuthZ implementation with OPA, so you won't need the enterprise license for that if you want to try it with Gateway. That works as well. There are 3 subgraphs on this demo that are just returning mock data. They're just using this great package from the Guild to return some mock data right now for this demo. And I have 2 entry points set up right now, one on a gateway that's totally open. And so if I try to run this query right now, I get everything back. I don't even have to send authorization because there's not even Authn or anything else on this one. So all these queries right now will always return no matter what my auth is. It doesn't really matter because this is a totally open supergraph. But on the router, we've implemented the OPA AuthZ that we're showing you. Let me get rid of this because we don't need that. And so if I try all queries, all fields here, this one that has everything on it, now that's not authenticated because our policy for micro frontend 1 only is allowing 2 different queries. It's allowing the payment method with some restricted fields, by the way, notice that, and then the plan by user for micro frontend 1. So if we go back here and we look at plan by user for micro frontend 1, that one is allowed. Now if we change the client to micro frontend 2, that's going to be denied. And notice we're getting our 401 status code returned here as well. If I turn the auth off, of course, it'll also be denied in the same way. For payment method, you'll notice this, maybe you'll notice, what do you think? For micro frontend 1, is this going to be accepted or denied? Any idea? This one's going to be denied because it has these restricted fields on it. Let's say this is maybe a micro front end that just has to show the payment methods. It doesn't need all this particular information about, the credit card numbers and the account numbers. It only needs to know the names of the payment methods, the names on the account to display maybe in a UI or something. And so once we take those restricted fields off, now that operation is allowed for that client. Again, if we change this to micro frontend 2, that one's not going to be allowed. And finally, this is micro frontend 2. This is the one it's allowed, lines by user, so that one goes through. If I change this one to micro frontend 1, it will not be allowed. So that's a quick little live demo, but you can play with that a little bit more on your own if you'd like. I'll show you that in a minute. For future development of, let's see, can we change that back to the slides? For future development of this, we're just kind of beginning our journey on this AuthZ project. But what we want to do is test it with a lot more load, a lot more clients, a lot more policies. Again, at T-Mobile, we're going to need to have thousands of clients that rely on this to do their AuthZ. And we want to test it with that kind of load on it to see what kind of performance we get from OPA and the external coprocessor. Right now, we're seeing about 100 to 200 millisecond latency. So for some of you who require really fast responses, that may impact things. With the mapping that we're doing in the policies, I don't expect to see that increase even with more load, with more clients on there. But we'll see as that develops. So, we want to swim with the sharks there or whatever. The other thing we want to do is maybe we can show a little more heart. Like maybe the operation is allowed, maybe the query is allowed, but the restricted fields, rather than failing the entire operation just because they asked for a restricted field, OPA can send back more than just a Boolean. It can send other data back to that broker service where the broker could actually sanitize the query and make that a little bit better. We're also looking at that life cycle of the router that we can also hook into the response. And on the response, we could maybe mask certain fields on a response. We could monetize the API by certain fields of external user of an API, which fields they request. OPA could send back monetization information for that. So we want to explore other things we can do like that, other additional usages. And finally, just other AuthZ hardening that we can do and walk alongside maybe even some of these other Apollo things. Like we mentioned, some of the directives that we could put on the subgraphs, that OPA could actually use some of those to make AuthZ decisions as well, to use the directives, the contracts, safe-listed, persisted queries, to use those in conjunction with the external coprocessor and open policy agent to make those decisions. So we'd love your feedback on what we're doing with AuthZ and on our presentation. So I think this will be up there afterwards too, because I also want to show you this last one, which says any questions, which, kind of tough if there are, because we've been told we can't take them right now. But if you do have questions, please reach out to us on LinkedIn. We don't have a topic table, so just stop us around the summit, and we'd be very interested and open to your ideas and your reaction to what we're showing today. That open source demonstration repo, please, you're welcome to download that from GitHub. It's GitHub, remember my middle initial, JR Barr, at that OPA Apollo demo up at GitHub. Please check that out and contribute to that as you see fit. So thank you for being here today. Enjoyed presenting to you, and hope you got something out of it, and hope you'll give us something back as we pursue this journey together. Thanks. Thanks, Manoj. Thank you.